This is a lot of work I've done in the previous year. I'm a Blue Waters graduate fellow, so a lot of the work was done with that. Some of it's kind of an extension of some work I did last summer at Sandia with Siva. Kamesh also helped out, he's my advisor. So graphs are everywhere. Pretty much most data is representable as a graph. Some major examples, obviously, the internet. You have pages, hyperlinks, the hardware running the internet, servers connected to each other, all pretty much just graphs. Nodes, vertices connected via edges to other vertices. They're also pretty pervasive throughout all of sciences, chemistry and biology, even, say, scientific computing, modeling. Anything that uses a mesh is more or less just a kind of different graph. As well as you have social networks like this one right here, which I believe is my advisor's LinkedIn network, so his connections to other people. So in addition to graphs being everywhere, they're also big. So the internet, the indexed internet by Google is about 50 billion pages, trillions of hyperlinks. So that's pretty big. The actual internet itself is much, much bigger. Most of it's not publicly accessible, but you're looking at trillions and trillions of pages. Facebook, just Facebook, has almost 1 billion users, hundreds of billions of friendships between the users, as well as the human brain. I think this has been talked a lot about throughout this symposium, but it's about 100 billion neurons, about 1,000 trillion synaptic connections. So going forward, one of the big challenges is just how do we actually analyze networks of these scale? Because even the human brain, you look at Blue Waters, I think it has about a petabyte of memory total on the whole system, give or take. Just to store the structure of the brain graph would be several times that, maybe another order of magnitude, so 10 to 20 petabytes. In addition to being everywhere and big, they're also very complex. So they're listed, DARPA considers them very challenging. They're listed as one of their toughest mathematical challenges. I believe computation, just general computation at scale, is also on this list. I think that's from 2010 or 2012. And graphs, just the complexity, as you can see, when you increase the number of vertices, the number of possible graph structures gets pretty big, 2 to the n squared, which is obviously a lot. As well as just real-world graph characteristics, they all tend to have certain kind of things in common that make them especially difficult for computational analytics. So one of the things is what's called a skewed degree distribution. So you have some vertices with, say, millions of edges, other vertices with 1 or 2. So when you're trying to distribute work among processing elements with that kind of graph, it's very tricky, because you don't want one processing element to get all the big vertices with all this work to do. Other processing elements get all the small vertices, and it just sits around idle waiting for the other processing elements to finish up. And additionally, what's called small world nature. So looking at Facebook or Twitter, you are within about 5 hops to any other person that uses services. That's generally what's considered for all of humanity. You're within like 5 to 10 hops any other person on the planet in terms of like social connections. So that additionally makes things difficult from more of a computational perspective. Makes distributing work difficult for a lot of reasons that I'll talk about, as well as for storing it in memory. It makes it very inefficient. I believe in the last talk it was talked about latency issues. You have very poor cache performance with most small world graphs, so that just makes things even more slower. And one final point, I'm not going to talk about this, but most graphs are dynamic. You have vertices coming and going, edges coming and going. So that just makes, adds another layer to the computational difficulties with processing graphs. So I worked pretty much on 3 different sort of mini projects during the course of the fellowship. Consider them just challenges and goals I had for overcoming these challenges. So as I talked about, parallelization is very difficult. So at the lowest level, I first considered node level optimizations. So we have these skewed graphs. How can we parallelize them? I especially considered using many core processors, because that's just the general direction computation is going. More cores per node. So I looked at possible optimizations just for these very parallel per node level architectures. Then going up in scale, I have graphs stored in distributed memory. So this is related to the small world nature. Partitioning is very difficult for small world graphs. Ordering is also very difficult just because everything's so close together. It's possible to find a way to make them, get some locality out and keep vertices grouped together so that you're only working in a certain portion for a given, say, MPI task. As well as what partitioning objectives or constraints should we look at to kind of optimize computation or minimize computation and communication times, and look at it across a wide variety of different analytics, both simple to complex. One final challenge, I guess we're a little cut off here, as well as kind of putting these together. So you have, say, node level optimizations, distributed optimizations. How can we put these together and take a massive graph and actually run some analytics on it and glean some new novel information that wasn't possible before? So going back to the many core optimization stuff, I was specifically more focused on GPUs here rather than Xeon-Phis. So essentially, it was kind of mentioned briefly in the previous talk, graph algorithms tend to follow a very fixed structure. It's tri-loop structure. Just ignore all the arrays and subscripts. Those are just there to confuse you. So you have a basic outer loop with some iterations. It's dependent on either graph structure or like some stopping criteria you have for your algorithm. Some middle loop, which is over a work queue of vertices. So it could be dynamic or it could just be every single vertex in the graph. As well as you look at each vertex in this work queue and you have to look at the edges connected to that vertex. So parallelizing this is tricky because we have the skewed degree distributions. So going through one iteration of this loop here is not equivalent to the next iteration or another one. So parallelizing it over here can result in severe imbalance, either on a single node between threads or, say, between tasks. Parallelizing here isn't really all that great either, just because, as I mentioned, some vertices only have, say, a single edge, so you can't really parallelize across that. So we looked at a few different ways to kind of get around this, kind of improve parallelism. These are based off of previous work, what I like to call hierarchical expansion. Every single person calls it something different, but it's essentially differing parallelism between these two loops, just based on how many edges a given vertex has. So you look at the vertex, and say on a GPU, you can do per warp, per multiprocessor, or per thread, or globally parallelize across the edges on that vertex. What's called the Manhat Collapse. So it's taken these two loops. Well, firstly, the local Manhattan collapse. So what we do is we have a single multiprocessor in our GPU. It grabs a chunk of vertices from this loop, and then more or less collapses the loop for those vertices, collapses these two loops for those vertices, and parallelizes across that. There can be some imbalance introduced since you're still kind of dependent on this loop, but overall it works pretty well. As well as, say, the global Manhattan collapse, which is just collapse of both these loops in total, just to introduce all this new parallelism, so each processing element at all the different levels, work, thread, multiprocessor, are all getting the exact same amount of work to do. So nobody's sitting idle, everyone is able to get everything done at the same time. As well as in considering all these three, I just looked at a bunch of general case optimizations, which are pretty much applicable to not only this, but any work on GPU. So it's just memory considerations, cache, using the explicit shared memory, as well as using warp based primitives, so like team scan and stuff like that. So for the results, here this is for breadth first search, was more or less the simplest graph algorithm you can really look at. So we implemented this and a few other ones. I'm just showing this just because. So here is the results for these three. So you have hierarchical, local, global. By far, we noticed the best performance with the local collapse, essentially because it's better able to exploit cache locality, shared memory, versus the global approach where you're constantly reading from global memory. And we observe, just for GPU, these bars are the baseline, which just parallelism across the second loop. So we observe, I think, like 7 or 8x speed up versus the baseline, and up to about 3x speed up versus optimized CPU code, which is pretty good. As well as here's just the effect of the various optimizations. Nothing really great here to note, except that any given one optimization really doesn't help. You got to do everything to really get much performance benefit. All right. So going on to the next level, we're looking at distributed memory. So partitioning. So it's a very challenging problem for small world graphs, as I mentioned. You want to really balance the partitions with the number of vertices and edges, as well as minimize the edges, as well as the edges coming out of any given task. What this does is when you balance the edges and vertices, that's more or less equivalent to the amount of work any given task has to do. And the edges coming out of a given task is more or less the amount of communication that task has to do. So you want both to be really balanced in terms of minimizing computation communication. Additionally, we looked at ordering, which is, all right, you have your partition, each task gets some chunk of vertices and edges. How do we actually store those vertices and edges on that task to get the best and optimal performance? So for partitioning, we used Pulp Partitioner, which is something I developed last year. It's really the only partitioner that's able to scale to massive graphs and do multi-constraint, multi-objective partitioning. As well as ordering, we used traditional numerical analysis methods that are commonly used for linear algebra kind of things. So bandwidth reduction like RCM, as well as implemented a few, I guess, call them graph-centric approaches, just based off breadth first search, trying to maximize locality based on that. And we saw pretty good speed ups here for partitioning, and some still pretty good speed ups just for ordering. And these are more conservative in terms of the fact that these are the worst case speed ups, so it's the slowest task to the slowest task, speed up for that. So the average speed up is probably a bit higher. So really the only thing gleaned from this is that partitioning is obviously more important in a lot of the ways. I mean, it's really dependent on the algorithm. If your algorithm is very communication dependent, then obviously this is going to be even more so dependent. If it's a very simple algorithm, then you might want to focus on the ordering instead. All right, and then putting it all together for large-scale analytics. The reason we want to do this is a lot of current big data approaches uses external memory. So like MapReduce and everything, you're just constantly writing to disk or flash. And that can be slow if you don't have like a commodity cluster of like 20,000, system or 20,000 nodes. It'll take forever. So yeah, using the optimizations, I looked at the largest currently available public local graph, which is about 3.5 billion vertices, 30 billion edges. That's, to give it a sense of scale, that's about the size of Bing's index. So about a tenth the size of Google's index, which is still a good chunk of the web. And this is the first known work that's actually been able to run this on distributed memory versus, say, external memory. So yeah, we were able to get it to run on only 256 nodes instead of just like trying to scale it hugely. First, we want to see, okay, we only have this size of a system. How can we best get it to run here? Just see, smallest case. So in a minimum of 256 nodes, which is more or less memory dependent, we were able to get it run, and we implemented several simple to complex algorithms, and got it to finish up in minutes. We did some community detection, which was probably the most complex algorithm. And something we noticed was that similar to, say, degree distributions, communities also tend to follow this kind of scale-free-ish distribution with a very heavy tail. So just a summary, we got pretty good speed-up results for the GPU work, some good speed-up results for running the analytics in the distributed sense, as well as I just mentioned, we're able to complete our analytics suite on the large web crawl. So just another summary, these are some of the publications. This is the many core optimization work that's going to appear in IPDPS, as well as the layout work that's currently under submission, as well as this. If you're at IPTPS, I'm also going to be presenting a poster on this, and I'm planning on submitting a poster to SC, kind of based on this too. So in conclusion, as I mentioned, real graphs, big, complex, difficult to do all this cool stuff with. A lot of challenges just for general parallelization on supercomputers specifically. So yeah, I just showed you what I did with the fellowship going forward. Hopefully this will enable scaling to future larger graphs, larger systems, just general supercomputing stuff, everyone says. Yeah, like to thank Blue Waters, NCSA, fellowship, and thank you.